Let's take a look now at the idea of evaluating limits analytically. First, like usual, let's take a look at the learning objectives. What is that we want to get out of this next section here? The first thing is we want to be able to evaluate a limit using properties of limits. So that means that we're going to end up talking about some of these properties of limits that are very, very useful in trying to actually evaluate a limit. I want to develop and use a strategy for finding limits. Evaluate a limit using rationalization techniques, being able to rationalize a rational function, and evaluate a limit using what's known as the squeeze theorem. So we'll discuss exactly what the squeeze theorem is. So let's start off with the idea of some very useful properties of limits. Now, you can use these properties without proof, unless otherwise asked. It's possible that I may ask you during a quiz or an exam to actually prove one of these properties. You never know. So you should be extremely comfortable with these properties and be able to logically sketch out some type of proof as to why these are true. So let's start off with I need to let B and C, these two numbers, be real numbers, and let n be a positive integer, and f and g be functions with the following limits. As x approaches c of f of x, the limit as x approaches c of f of x equals L. L is also a real number, and the limit as x approaches c of g of x is k, which is also a real number. So both L and k are elements of the real numbers. So, number one, the limit of a constant function. The limit as x approaches c of the constant function b is simply equal to b. And if you sketch something out that would represent this thing, that should actually make sense. Here's xy axis, and here's the line y equals b. It's a constant function, right? It's a horizontal line. So as I approach c, let's just say c is right here. As I approach c from the right, well, the value of y is always b. As I approach c from the left, well, the value of y is also always b. And it's continuous, so the limit is clearly going to be simply b, because it is a horizontal line. It doesn't matter where you are, the value will simply always be b. Okay, scalar multiples. The limit as x approaches c of b times f of x will equal b times L. Remember, L is the limit as x approaches c of f of x. So f of x approaches L. So if I take some constant function or constant value b and multiply it by f of x, all I'm really doing is multiplying the limit L by b. Now, one way to look at this is I can take this limit and I can write this as b times the limit as x approaches c of f of x. Well, we know that this piece is going to be L because we said so right here. So it's just b times L. The sum or difference. If I take the limit as x approaches c of some function f of x plus or minus some other function g of x, well, if the limits for f of x and g of x are both defined, and they are because we said it's L and k, then this must simply be L plus k. And the logic behind that is simply I can rewrite all of this as the limit as x approaches c. Actually, I said plus. This should be plus or minus to match what I have right here. But this is a limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. Well, we said that this is L and this is k, so clearly this has to be L plus or minus k. Okay, a couple more here. The product. Now again, assuming that these limits of f and g exist, which we said they did, they're L and k, which are real numbers, then the limit as x approaches c of f of x times g of x will be L times k. That kind of makes sense because I can rewrite this thing as the limit as x approaches c of f of x multiplied by the limit as x approaches c of g of x, and clearly that is L times k. Now the quotient, here the limit as x approaches c of f of x over g of x will equal L divided by k, which is probably what you suspected. This provided, and we have to have a caveat here, I'm going to say for k non-zero. Remember, k is a real number. We said k could be any real number. Where here, k can't be any real number. The limit as x approaches c of g of x has to be non-zero. Now again, I can rewrite this as the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. And from that, I think you can clearly see that's L over k. Again, I have to specify k has to be non-zero. Powers. The limit as x goes to c of f of x raised to the n, this is going to be L raised to the n. And I think you can see that a little bit better if we rewrite this limit. I can write this limit as the limit as x approaches c of f of x. Rather than f of x to the n, it's the entire limit to the n. See, these are equivalent. Well, clearly, if the limit as x approaches c of f of x is L, then this must be L to the n. Now, there's 6 different properties for evaluating limits that will come in extremely handy with trying to evaluate other limits. You should memorize these. They should be absolutely immediate.